Hey class, welcome back to chapter 23, linear programming. Today we'll be looking at the final exercise, exercise 23D, objective functions. There's quite a bit to get through in this one, so feel free to pause, take notes, or come back to it later as you need. Okay, so when we talk about linear programming, we're talking about maximizing or minimizing linear quantities subject to specific constraints. And those constraints are typically represented as inequalities. So for example, if I'm running a business, I might have a certain amount of income that I need to make each month to keep that business up and running. And it might be that the number of staff I can hire at any time has a maximum range, so I can have a little bit less than that, but I need to sort of work within that range to be able to make the money that I need to make. Or I might need to have a minimum number of staff to be able to make the money required to keep that business open as well. So we're sort of looking at a few different constraints in that problem alone. We might also within that need to make a certain number of sales or any sort of thing. So a lot of business functions within linear programming, okay, or a lot of business applications. Our constraints define the feasible region in this topic, okay, and in that feasible region, that's where we will maximize or minimize the quantity. To do that, we need to evaluate what we call the objective function for all of the corner points of the feasible region as per the corner point principle. So the corner point principle states that for all of the corner points of the feasible region tends to be where we find either our maximum or our minimum for that function. So we don't need to assess every point in the region, just the corner points. We're going to start with a really quick example. We're going to find the maximum value, and here we're given the objective function as z equals 5x plus 3y, given the constraints as shown in the feasible region below. So our first step is to evaluate the objective function for each corner point. Doing this in a table is recommended. We're going to excuse the typo on the screen. So the way we do that is we're going to set up our table. We're going to list our points. And then we're going to evaluate for each of our objective functions. For our objective function at each point. And in this case, our objective function is z equals 5x plus 3y. Okay. So setting it up as a table, you can draw a big box around it if you really like as well. So we're going to look at our corner points. It doesn't really matter what order we do them in. We can start at the origin because it's the easiest one. And here on the graph, only the corner points have been labeled. So if we look at our first point, 0, 0, okay, if we substitute that in for z, we get 5 times 0. And remember, these are x and y coordinates, okay? So x equals 0 and y equals 0 plus 3 times 0. Well, that's all just 0. Okay, if we look at our next point, I'll move clockwise around the screen, so 0, 80. Okay, we again evaluate, we get 5 times 0 plus 3 times 80, which here is going to be 240. So the 5 times 0 cancels out, 3 times 80 is 240. You can use your calculator for this. We continue to move around. We look now at this corner point here, 60, 50. And again, we evaluate z equals 5 times 60 plus 3 times 50. You can do this in your head if you want, or you can do it using a calculator, but 5 times 60 is 300, and 3 times 50 is 150, and when we add those two together, we get 450. And then finally, our last point here at the bottom of the screen, 85, 0. Substituting in for our objective function gives us 5 times 85 plus 3 times 0. And of course, 3 times 0 is 0, and 5 times 85 is 425. Now, we were looking to maximize, find the maximum value of the objective function. From this table, now that we have evaluated only the corner points of the feasible region, so it's really important we've only looked at these ones, and not the ones I'm about to highlight in the screen in red. Okay, we haven't looked at that point, and we haven't looked at that point because they are not corner points of the feasible region. Okay, they are just other points on the graph. They do not contain, or they're not included in the feasible region, so we do not consider them. Okay, for the maximum value of the objective function here, we have 450, which occurs at the point 60, 50. So we state our solution. Going back to my pen really quickly, the maximum value, and we write it as a sentence as we like, the maximum value of the objective function sorry, my pen is loading very slowly today, is Z equals 450, which occurs at, or occurs, when X equals 60 and Y equals 50. Sorry, my pen is loading so slowly that the 60 looks a little bit like a 66. So we'll just fix that up really quickly. And that's it. So that's how we determine the maximum value of an objective function. Okay, that's the basics. Feel free to pause here, take down these notes, rewatch whatever you might need, okay, before we jump into a much larger example of objective functions and linear programming. Okay, we're now going to look up setting up and solving linear programming problems. Okay, so we're jumping straight in with an example for this one. What we're going to find is that this example puts together everything that we've done so far in this chapter, and a little bit from our linear relationship stuff previously, of course, because we need it to graph inequalities. Okay, so in our example, we have a chocolate manufacturing company that produces only 2 types of chocolate, semi-sweet and bittersweet. Both chocolates require ingredients of milk and chocolate only. And to manufacture each unit of semi-sweet and bittersweet chocolate, the following quantities are required. Okay, and those are now on your screen in the table. What you'll notice is that we have a total of milk in kilograms available each day and a total amount of chocolate in kilograms per day. Okay, so each chocolate needs a certain amount to satisfy that flavor combination. Okay. So, or to make each kilogram. All right. The manufacturer wants to maximize the profit he achieves from making these products. From selling each of these products, he earns $7 per kilo of semi-sweet chocolate and $5 per kilo of bittersweet. So that's what's being represented in the table there. Okay. We need to decide how many kilograms of semi-sweet and bittersweet should be made each day to maximize his profit. So, really big question, lots of information. We're going to need this lot of information, so the data that was given first, we need that first. And our first step is going to be to define the variables, okay? So we're going to let X, and we'll just use X and Y, okay? X, I don't know why I wrote equal, okay? Let X be, makes a bit more sense, I think. Let X be the amount in kilos of semi-sweet chocolate, or just semi-sweet, produced each day. Okay. And Y can be the amount, also in kilos, of bittersweet. Okay, so all I've done here is I've made it very clear to whoever is marking my work later what each variable is. Okay, so I've said X is my semi-sweet and Y is my bittersweet. We now need to list the constraints. Okay, so from this table, quite literally, if I look at my constraint for the amount of milk that I can use each day, okay, because maybe that's just what's available shipping-wise each day, I don't know, right? I need 0.4 kilograms of milk to make semi-sweet and 0.2 kilograms, not kilograms, of milk to make bittersweet chocolate. Okay, so 0.2 Y. My total amount available is 50 kilos. Now, I'm not going to have it equal 50 kilos. I might not need the whole amount each day, okay, or I might not, I just can't exceed it, basically. I can use less than it, but I cannot exceed it. So that helps me decide what this what inequality I'm using. Okay, so it's less than or equal to. I can use up to 50 kilos. I can use the whole lot, but I cannot use any more than it because it's not available. My other constraint is chocolate. So in the same sense, okay, I can use 0.6 kilograms of chocolate to make semi-sweet. I can use 0.8 kilograms of chocolate to make bittersweet, and my total amount available of the chocolate ingredient, or maybe it's chocolate powder, whatever it might be, is 120 kilos. So again, I can use the whole amount, or I can use less than it, but I cannot exceed the 120. I also need to remember that I have constraints whereby X is either greater than or equal to 0, or Y is greater than or equal to 0. So I can produce no semi-sweet, I can produce no bittersweet, or I can produce more than an amount of it, but I cannot produce a negative amount of either of those. Okay, so those constraints are both greater than. Very rarely will these constraints not exist, and typically in real life situations you can't have negative amounts. We don't want negative amounts, so they tend to be X is greater than 0, Y is greater than 0, or X is greater than or equal to, etc. All right. So we've listed our variables. We've allocated X to the word semi-sweet and Y to the word bittersweet, so we don't have to keep writing those words over and over. We've listed our constraints. We have 4 of them. Okay. Our next step, just like we did in the previous example, is to graph the feasible region, and we want to label all corner points. You can do this on your CAS instead of me trying to draw it out for you today because that would be painful. I've prepared one earlier. So we've graphed the first equation, okay, here in blue. We've graphed the second equation here in green on the screen, and all points have been listed, including the X and Y intercepts, but we know from the previous example, these are not corner points of the feasible region, so we won't need to include them in our next steps, okay? Moving forward, we now need to define and evaluate the objective function, and I've got the graph on the screen from the previous example as well. So our objective function for profit is profit, which here is going to be P, because if we remember back to our previous information at the beginning of the question, we wanted to maximize how much money we were making through this chocolate manufacturing each day. And the objective function is given by, well, again, remember that semi-sweet is given the variable X and Y is given the variable, is given to bittersweet. So we can make $7 per kilogram of semi-sweet and $5 per kilogram of bittersweet. So that's our objective function, and that's where that comes from, is the profit function. So this is our objective function. Okay, and we've now used all of the data given at the beginning of the question. We now need to define and evaluate the objective function. So we've done the defining, we've sorted that out, we've said this is the objective function. We now need to evaluate it for each corner point. So again, I'm going to set up a table, and we're going to evaluate it for P equals 7x plus 5y, okay, as our objective function. So the first point, again, I'm going to start with 0, point A listed here on the screen, okay, just because it's the easiest to substitute, equals 7 times 0 plus 5 times 0, which of course equals 0. Our next point, moving around, we go to B. So that was A, point B, 0, 150, okay, remembering again, these points, we don't need them because they're not corner points of the feasible region. Okay, so for that point, we have P equals 7 times 0 plus 5 times 150, which gives us 750. Okay, we go to point C next, which is over here, okay, which is 80, 90, and we evaluate again for P, so 7 times 80 plus 5 times 90, which is 1010. And finally, point D down the bottom here, 125. Oh, just fit this in. P equals 7 times 125 plus 5 times 0, which gives us 875. Now again, we needed to find the maximum, okay? And here our maximum is $1,010 per day, which occurs at the point C, which conveniently is the same point as previously. Okay, so now that we've identified the objective function, so we had to define the constraints, We had to define the objective function. We needed to plot the graph to find the corner points of the feasible region to evaluate our objective function, because this point here is not going to randomly be our maximum point, okay? It's always going to be one of the corner points, okay? So we don't have a random point in the middle of the feasible region. We look at one on the edges and specifically the corner points. We can now state our solution. So the maximum profit, which is what we were looking for. The max profit is $1,010 a day, okay, or just 1,010, which is obtained by producing. You might notice some similarities in the way that I've worded this answer to the previous example, okay? The maximum is, which is obtained by producing. We had it at the point 80. So 80 kilograms of semi-sweet or semi-sweet and 90 kilograms of bittersweet chocolate. Sorry, it's loading so slowly, I cannot see what I'm writing. Chocolate each day. And that's it. We've solved our linear programming problem, okay? So similar steps as what we've worked through in the first example, okay? We needed to define our constraints, which was given to us at the beginning of the question. We needed to define the objective function. We need to plot all constraints on the graph and find the corner points. That can be done on your CAS, including with the feasible region, okay, and the shading for the region. And then we evaluate for each corner point of the objective function to decide what our solution would be. So 5 steps to that one. Some of them are quite large steps, yes, but definitely the same steps for every single situation. All right. Feel free to go back, pause, replay as much as you need from that. Apologies that this video is incredibly long, but there was quite a bit to get through. And as always, guys, if you have questions, let me know. But otherwise, best of luck with the work, and I'll speak to you all very soon.